So I'm now going to talk about linearization, and this is a particularly interesting and important topic when we're studying state space models. And the reason is because state space models basically use linear algebra. So we need linear models in order to be able to use all these mathematical techniques to design state space models and build controllers and do all these things we want to do with them. But most of the things that happen in nature do quite often have non-linear aspects to them. And you can just think back to the pendulum, right? The pendulum, when we're deriving the equations for something like that, there's going to be things like sine theta and cos theta in there, and we have to linearize in order to be able to analyze them using these methods. So one way to linearize systems is going to be around some point. We have to say that this is a nonlinear function, but around certain points we want to have a little local linear model which actually works quite well. And typically what we'll do in control engineering is do that around equilibrium points. And the reason for that is we quite often want to operate things around equilibrium points. So we think back to our inverted pendulum. What we're doing is we're balancing this pendulum. Normally in the inverted condition it's in an unstable equilibrium. It's going to be standing up and it would fall down if it wasn't for the controller. There's another equilibrium, of course, when it's dangling downwards. So these are the two conditions that we have to consider as being equilibrium points for a pendulum, and that's generally where we want the system to be. So it makes perfect sense in this case to say let's basically linearize around those points because those are the ones we want to use. You can also linearize about any point in general because that's the idea of linearization. So what we want to do then is we want to take our nonlinear model and say around a point where I'm interested in, I want to linearize it, and then I can use my mechanisms of state space analysis and state feedback control design and build a nice controller which will work nicely. So given a nonlinear model, first thing we need to do is find out the equilibrium position, right? So when is something at equilibrium? Well, if you think about it, just think in terms of the pendulum again, it's at equilibrium if it's not moving, right? If it's staying still. It would stay still dangling down and intend to give it a knock, but then it won't be at equilibrium anymore. Or it can stay still in the unstable position as well, but just a single air molecule knocking against it and it might go off. But basically, it's at equilibrium when the differentials are zero, right? So the way to find equilibrium is to say, let's look at our model, let's look at the differential of the system with respect to time, so x dot. When that's equal to zero, we could find an equilibrium position. So having found equilibrium positions, we then want to linearize around them. So how can we do that? And one way is to use a Taylor expansion, right? So first of all, let's think about state space models in general, and we have the general form for an element in a state space model such that x dot equals some function. So let's call x the state. dx dt equals some function of x. Now, in a nonlinear system, it's going to be a nonlinear function of x, but we want to get that to be a linear function of x. So we're interested in state space models being first differentials because a state space model is built up of lots of first order differential equations, and we can use lots of these first order equations in order to actually represent a high order differential equation, and that's the whole point of state space models. And we can write them in matrix form with vectors for states, and it's a very elegant framework to use. So we're going to basically we're concerned with first order differential equations, and we want to break things down into first order differential equations. So we can start looking at a Taylor expansion around a certain point. We're going to call it XS, the operating point. It's going to be the equilibrium. So what we're going to do is say, let's look at the Taylor expansion of a function around point XS. And the Taylor function is given by, the function in general is given by the function value at that point, XS, plus the differential of that function at that point multiplied by the deviation we are away from that point, plus the second differential at that point multiplied by how far we are away from it, and so on. It goes up higher order terms. But what we're going to do is we're going to say we only care about the first order terms, right? And that's fair enough because the other ones become less and less important anyway. And as, basically the deviation from the point that you're interested in becomes smaller and smaller, their effect is less and less anyway. So we're going to throw out everything other than the first order terms, and we end up then with a function. A function of x is given by the function value at this point xs multiplied by the gradient at that point multiplied by the difference, well, how far we are away from that point, right? So that's the first thing. Now also, we've already said we're interested in doing things now at equilibrium positions. And at equilibrium positions, we know that our function is actually going to be 0, right? So we've already said that we're going to do it such that dx dt is going to be 0 at that point. So our first order Taylor approximation basically loses its f of xs term, right? So we end up with an expression saying our function now is given by the gradient at the equilibrium position multiplied by how far we are away from it. And that's very important. So gradient of equilibrium, deviation from equilibrium. So we can think about this a little bit more graphically as well. We can think, let's look at this blue nonlinear curve, and what we're trying to do is approximate it with a linear curve, right? We just want basically to say, look at point x0, y0, that's there, and we're going to say, let's approximate at that point this by a gradient, which is going to be effectively a linear straight line at that point. So how can we work out what that point is? Well, what we have to do is we have to work out the gradient at that point on the curve, right? So if we've got the analytical expression for the curve, we can work that out. dy dx, we can work that out. And basically, dy dx is also, for very, very small deviations away from that, is going to be given by a little change in y divided by a little change in x. So let's take that a bit further. Imagine we've got the gradient dy dx at that particular point, y0, 0, 0. For a tiny little deviation, we've got effectively a relationship that we can say is as follows. Well, first of all, this is definitely true. y1, the second value, is going to be the original value plus delta x. X1 is x0 plus delta x. Y1 equals y0 plus delta y. And because we're only a little way from the actual point we calculate the gradient we can assume is appropriate over that range. So we can say the little change in y1 minus y0 is the gradient multiplied the little change in x. And that's only true as long as delta x and delta y are really, really tiny. Okay, and then we've got this linear approximation. Now, that's just for a one-dimensional case, of course. In general, we've got multi-dimensional cases. So we're going to have several parameters x, first of all, and we're going to have maybe multiple functions as well, right? So what we're going to have is some function of this vector x is going to be one function or another function of this. So we end up with basically matrix equations. And what we need to do is we want to do the matrix version of looking for how do we get the gradient, and we end up with something called the Jacobian matrix. Let's just think in terms of just a surface here. This is a surface, and of course in this particular case it's got an x and a y and a value as well. And if we want to approximate the gradient on this surface, then obviously it depends what direction you're going in. If I was going, let's go along this direction, then we've got one gradient, but also going orthogonally to that, we've got a different gradient. So for a particular point on this particular surface, our gradient is no longer a line, it's actually a plane. And as the dimensions go up, we end up with hyperplanes, and you can't draw them because obviously we haven't got enough dimensions in the world. Basically then, what we've got is the situation such that we want to calculate this Jacobian matrix, and this is composed of the following. It's composed of the rows correspond to different functions, right? There's different functions of the parameters going down in the rows, and across for the different columns we're differentiating with respect to different dimensions, so how this thing is actually changing with, in this case, x1, x2 and x and n. So we end up with this multi-dimensional representation for this particular Jacobian matrix. And what we need to do to calculate this is just to, we need to know what the functions are, and we need to differentiate them with respect to the parameters that we're using here. And this will become a lot clearer now when we actually go through an example. Imagine we've got a function of two variables, x and y. So because of that, we've actually got two rows in this column. This is one function, this is the second function, and we've also got, in this particular case, we've got two variables, we've got x and y. So we need to calculate, first of all, the derivative of the first function with respect to x and then with respect to y, and then the second function with respect to x and with respect to y. So let's do f1 x of y is going to be given by the first function here, x squared y divided by 2, and the second function, the second row, is going to be x plus sine y. And then basically the Jacobian then is going to be differentiating the first function with respect to x and y for the top row, and for the second row it's going to be differentiating the second function with respect to x and y. And these are all partial derivatives, and if you remember, a partial derivative means everything other than the thing you're differentiating with respect to is considered a constant. So if you want to just see that in action for this particular example, it's quite simple. The first term, delta f, delta x, if you like, we differentiate this partially with respect to x. So x squared goes to 2x. So 2xy over 2 goes to xy. With respect to y, right, it's going to be x squared over y, right, because the y goes to 1. This one with respect to x goes to 1, and this is a constant, so it disappears. This with respect to y, x is a constant, so sine y goes to cos y. And we just pop those values in, and we've got the Jacobian for this particular function with respect to its parameters.